Hello viewers, welcome back to our channel. In the last lecture of field theory, we have proved that Zn with respect to two operations, addition and multiplication, it forms a commutative ring with unity. Okay students, so in this lecture we will show that this Zn is a field if and only if n is a prime integer, and as like the last lecture we are using here the method of division algorithm. Okay, so first rewrite again what is Zn. Zn is the set of all remainders of n, 1, 2 up to n minus 1. Okay, and we have proved that it is a commutative ring with unity one with respect to these two operations. First is addition. We have defined this operation as the remainder when a plus b is divided by n. Similarly, the multiplication operation is defined as the remainder when AB is divided by n, and we have seen in the last lecture that it is a commutative ring with respect to these operations, and it is a commutative ring with unity. Okay, now let us define a set Zn cross. So here we are collecting the non-zero element of Zn who are co-prime with n. So what is this set? This is a non-zero element of Zn which are co-prime to n, and of course this is a subset of Zn. Okay, so now we will show that this Zn cross is an abelian group with respect to multiplication. So what is our claim? This Zn cross, and with respect to this operation, is an abelian group. For this, what we have to show? We have to show that it satisfies closure, associativity, existence of identity, existence of inverse, and commutativity with respect to this operation multiplication. Okay, so first we establish that it is closed with respect to this multiplication operation. Okay, for this let's choose two element a and b belongs to Zn cross. So this implies what are a and b? These are non-zero element, and these are co-prime to n. Okay, now we want to see that whether their product belongs to Zn cross. So this is our target, whether this multiplication gives you an element in Zn cross. So let's assume their product is some element c. So if first we see that if c is 0 or not, c can be 0 or not. Okay, if c is 0, then a combined with b is 0. This means this is the remainder when AB is divided by n. It means you have divided AB by n and you are getting remainder 0, and this implies n completely divides AB. okay, which is not possible. Which is not possible. Why it is not possible? Because A and B both are co-prime to n. Okay, therefore n cannot divide their product. Okay, so this establishes that C cannot be 0. Okay, so C cannot be 0. Therefore, now we will show that this C has GCD 1 with respect to n. Okay, C is co-prime to n, and if we are able to show that, then definitely A multiplied by B belongs to the set Zn cross. Now we wish to show that this we have to show that the combination of A and B is C and C is co-prime to n. This we want to show now. Okay, so let if possible C is not co-prime to. Okay, this implies C and n has some GCD D and D is greater than 1. So this implies by number theory there exists a prime P which divides D, because GCD is not 1, therefore you can always find a prime P dividing D, and this implies this prime P divides C and this prime P divide N as well. So it will divide both C and N. Okay. Now if you see that what is C? C is the remainder when AB is divided by N. Okay, so it means you can write C as AB minus NQ, where Q is the quotient. Okay, now P divides C and C is AB minus NQ. This implies P divide AB. Why? Because P also divide N. Now P is dividing C. C is equal to AB minus NQ. Therefore, P is dividing C and P is dividing N. Therefore, P divides AB. But P is a prime. Mind it, P is a prime. Therefore, either P divide A or P divides B. Now, P divide A and P divide N implies the GCD of A and N cannot be 1 because you have a common divisor P. Similarly, P divide B and P divide N implies B and N cannot be co-prime. So these are two contradictions. Why we arrive at a contradiction? Because we assume that C and N is not co-prime. So therefore C and N must be co-prime to each other. So this implies if you compose A and B, the result is C, and C is non-zero. C is non-zero, and C and N they are co-prime. Therefore, we may say that very surely this combination belongs to the set Zn cross. So this establishes the closure property. Now, since Zn cross is a subset of Zn, therefore associativity and commutativity in Zn cross follows from Zn, because it is a subset of Zn cross is a subset of Zn, and Zn is a commutative ring with unity. Therefore associativity and commutativity follows from Zn. Okay, so what we have shown? We have shown closure associativity and commutativity. Now, existence of unity in Zn cross. So choose any element from Zn cross. Clearly, 1 belongs to Zn cross because 1 is non-zero and 1 is co-prime to n. Okay, so and if you see that is nothing but A, and similarly this way also. Okay, so it means 1 is unity in Zn cross as well. Okay, so 1 is the unity of Zn cross. So now we move to the existence of inverse in Zn cross. Existence of inverse in Zn cross. For this, choose any arbitrary element. A belongs to Zn cross. What can you say about A? A is non-zero and less than n. So it means A lies between 1 and n minus 1. Okay. Now, and moreover, the GCD of A and n is 1. So by using the result from number theory, there exist integers x and y such that ax plus ny is equal to 1. Okay. Now we focus on this x because x and y, these are ordinary integer, they may be positive or negative. Okay, so we want to see that what is the inverse of A. So we focus at x. So let x is equal to, divide x by n. What we have done, we have divided x by n, q is the quotient and r is the remainder. 0 less than equal to r less than equal to n minus 1. Okay. This implies, substitute the value of x here in this expression, and this implies a n q plus ny is equal to 1. Okay, this implies ar minus 1 is equal to take n common minus aq minus y. Okay, so it means n divide ar minus 1. Now we want to see that whether this r is the inverse of a or not. And you see that the right hand side is a multiple of n, and if you divide the whole right hand side, you will get the remainder 0. It means r may be the inverse of a. But for this we have to check that whether r lies in the set Zn cross. Okay. So we have to just only show that r is co-prime to n. So let us consider the GCD of r and n is d. This implies d divides r and d divides n. Okay. So so if you focus at this equation, now we have d divide r and d divide n. Therefore d will divide any multiple of r and d will divide any multiple of n. It means d will divide the whole term at the left hand side of this equation. Okay, so this implies d will divide ar plus anq plus ny, which is 1, Okay, so this implies D divides 1, and you know that if D is dividing 1, this implies D itself is 1. Okay, this establishes that the GCD of R and N is 1. Okay, now what does star implies? Star implies that AR minus 1 is a multiple of N. Okay, so it means if you divide AR minus 1 by N, you are getting the remainder 0. So it means in the notation of multiplication, we can write this as one, because if you divide AR by N, you are getting the remainder 1. Okay, so this implies R is the inverse of A, and this implies A is invertible and its inverse is R, and R itself belongs to the set Zn cross. So this establishes that every non-zero element of Zn cross is invertible. So it means we have completed all postulates for an abelian group. It means Zn cross is a abelian group with respect to multiplication. So this implies Zn cross is an abelian group with respect to this operation multiplication. Now we move to our main result of today's lecture, that Zn with respect to this addition and multiplication is a field if and only if n is a prime integer. So we prove this result both ways. First, suppose that Zn is a commutative ring with unity because it is universal true. It is established result that it is a commutative ring with unity. And what is special here? N is prime here. N is prime. Okay, so what we are given? We are given that Zn is a commutative ring with unity and N is a prime. So we have to show that this Zn is a field. Zn is a field. So for field with respect to multiplication and addition, what is remaining to show? That every non-zero element is invertible. Okay, because commutative ring with unity is already there, so only thing we have to show that every non-zero element is invertible. Since in this case n is prime, therefore what is Zn? Zn is the remainders of p, 1, 2 up to p minus 1. Okay, and if we have any non-zero element belongs to Zp, this implies A is between p1 and p minus 1, and you know that if any number is less than p and p is prime, then it is co-prime to p. Any integer less than p is co-prime to p. For all 0 not equal to A belonging to Zp. It means every element is co-prime to p in Zp cross. This implies every non-zero element of Zp is co-prime to p. And in the few step backs, we have shown that if any element is co-prime to n, then it is invertible. This implies A has inverse for every and this implies ZP is a field. So this is the first part. When you have assumed that Zn is a commutative ring with unity and n is prime, therefore you show that Zp is a field. Now conversely, suppose that Zn with respect to this operation is a field. What we have to show? N must be prime. N must be prime. So we prove this result by contradiction. Suppose n is not prime, this implies n is composite. So n can be written as the two factors n1, n2, 1 less than n1 less than n, and 1 less than n2 less than n. Okay, so this implies n1 n2 are divisible by n. It means this product is divisible by n. Okay, so this implies n1 n2 gives zero remainder when divided by n, and this implies you can write in the multiplication notation as this 0. Clearly n1 is less than n, n2 is less than n, therefore both these two elements are in Zn, and Zn is a field, and you know that a field has no zero divisor. Okay, but here you are showing that product of two non-zero element is 0, and Zn is a field. You can say that Zn is an integral domain, and therefore n1 n2 their product cannot be 0. So it means this is a, since Zn is a field, therefore integral domain, therefore product of two non-zero element cannot be 0. So this implies, why this contradiction is here? Because we have assumed that n is composite, so n must be prime. So this completes the proof of this beautiful result, important result. Okay students, that's all from my side. This is the complete method by division of algorithm. We have shown that Zn is a commutative ring with unity, and Zn is a field if and only if n is a prime. Okay, so stay tuned for upcoming lecture. Thank you.